In this video, we'll start by creating a very simple Python application. Once it's ready, we'll start containerizing our app. We'll create our first Docker file and manually build a Docker image using Docker CLI. Then we'll run it using CLI as well and map container port 8080 to the localhost. Along the way, we'll test a few things, including environment variables. Then I'll show you how to convert the exact same Docker commands into a Docker Compose file. We'll discuss how to build and rebuild images using Docker Compose and how to map ports. Later in the video, I'll show you how to hard reload your app without rebuilding the image at all. First, we'll start with imperative approach. This means we need to tell Docker what we want step by step. Step 1 is to build the image. Step 2 is to run the image, etc. On the other hand, Docker Compose uses declarative approach. This means we describe the desired state in a YAML file, and Docker takes necessary actions to maintain that state. If we have the image, it will pull it. If not, it will use build block to build the image, run it, and expose necessary ports. We'll talk more about Compose features after I show you what we're going to build in this lesson. Next, we'll start using environment variables to provide sensitive data and configurations to our app. I'll show you 3 different ways of providing those variables. We'll also use .env files to provide environment variables, which is a common pattern in open source community. We'll talk about new Compose features such as secrets and why you may want to use them to provide credentials like passwords and tokens to the application instead of environment variables. I'll show you how to create a secret, define it in the Compose file, and provide it to the app. We'll use short syntax when using it in our app and more verbose syntax when we need to specify the mount target of the secret, because many open source projects expect configurations and secrets files to be mounted to a specific location on the file system. Next, we'll talk about how to separate source code from environment-specific settings using configuration files. With configuration files, you no longer need to rebuild your Docker image with hard-coded values for each specific environment. Traditionally, we used volumes to mount local configuration files into containers. Then, Docker Compose introduced a new feature similar to secrets with the same API. You can create top-level config element and mount that config into container. You can use a short syntax or define a mount target yourself. Next, if you decide to run stateful applications such as databases, you will want to persist data between container restarts. The old way of doing this is called bind mount. Using this approach, you would take a directory or a file on your local file system and mount it inside the container. Everything that the container saves in that directory would be saved on your local file system. However, this approach has limited functionality compared to volumes. Another more advanced and preferred way to persist data is to use volumes. While bind mounts are dependent on the directory structure and operating system of the host, volumes are completely managed by Docker. Volumes have several advantages over bind mounts. For example, volumes are easier to backup and migrate than bind mounts. You can manage volumes using Docker CLI commands or Docker API. There are many other advantages as well. Let's say you're actively working on a feature for your application and updating the source code. To test it, you would need to rebuild the image every time. In this part, I'll show you how to reload your application without rebuilding your Docker image. So whenever you make a change and save the file, application is immediately updated. For that, we need to create another Docker file optimized only for local development. Next, we'll add Postgres database to our Compose file and use volumes to persist data. Then I'll show you how Flask and Postgres can discover each other using compose service names as DNS. Additionally, we'll create a private bridge virtual network and put both Flask and Postgres into that virtual network. We'll follow some best practices by using compose secrets to provide password for the database and environment variables for other settings. In production, you would almost always place your application behind a load balancer. In this video, we'll use Nginx as a load balancer. We'll create upstream service and use default round-robin algorithm. In our case, we would have only a single backend instance, but in production on a single Linux server, you would use at least 2 Flask replicas. Following this pattern, you can deploy a 3-tier application as well. Nginx can be used not just for load balancing traffic, but also as a web server to host React or Angular front-end applications. To slightly improve security, we will create another public virtual network. We'll place Nginx and Flask in the public network and keep Postgres in the private network. This way, if the Nginx container is compromised, hacker won't be able to reach Postgres over the network. Also, I'll show you how to create dependencies using depends on. In this case, Flask application will start only after Postgres container. A more advanced approach is to create a health check. We would use existing /about endpoint and only start Nginx container after Flask app transitions to a healthy state. This approach is more reliable than simply defining the order in which containers created. Finally, we'll deploy this stack to a remote single Linux server. We'll make some improvements, such as using restart policies. Most importantly, I'll show you how to automatically obtain and renew a Letsencrypt certificate using Docker. This way, we would expose only Nginx to the internet, secure that endpoint with HTTPS, and keep everything else private. Using this exact approach, you can deploy any front-end application, such as React or Grafana, and secure it with HTTPS. By the end of this tutorial, you'll be able to build a 3-tier application locally, deploy it on a single remote Linux server, and start serving clients. To summarize, we'll start developing Flask application locally using Docker. Next, we'll add Postgres database and Nginx for load balancing. And we'll create public and private Docker virtual networks. Finally, we'll deploy this stack to a remote Linux server. We'll expose only Nginx to the internet and secure it with a TLS certificate from Letsencrypt. We'll also set up automatic renewal for the certificate. By the end of this tutorial, you'll be able to deploy a full stack to a remote Linux instance and serve real clients over the internet. Original Docker Compose command line binary was first released in 2014. It was written in Python and invoked with docker-compose command. You had to install it separately on your host using a package manager or by downloading a binary. This is referred to as V1 version of Docker Compose. At the top of the Docker Compose configuration, you would use version element. You could specify values from 2.0 to 3.8, referring to a specific Docker Compose file format. Also, we typically used a docker-compose.yaml file name for this version. Version 2 of the Docker Compose command line binary was announced in 2020. It was written in Go and invoked with the Docker Compose command. Compose v2 ignores the version top-level element in the compose.yaml file. This v2 version comes bundled with Docker itself. When you install Docker on your host or a laptop, Docker Compose is included. For v2, the recommended file name is compose.yaml. However, old naming conventions are also supported. You can even use -f flag to provide any file name to be used as compose config. The main takeaway is don't use the version to specify the schema, as it will be ignored anyway. and use Docker Compose binary, which is built into Docker itself. Now, let's talk about use cases. First of all, many developers use Docker Compose for local development. They try to reproduce a replica of the production setup on their laptop. For example, they may deploy a database, Redis, or any other dependencies that their application requires. This allows them to quickly start working on features or fix bugs without interfering with anyone else on the team. Also, many open source projects provide a Docker Compose file that you can use to quickly spin up the project locally and test it. So Compose is used for demos. Another use case is when you don't have a lot of clients. You can use Docker Compose to deploy production-ready applications on a single Linux server. If you need to scale, you can do so only vertically by adding more CPU and memory to your server. It's much easier to manage than distributed applications. Another use case, which is rare these days, is to use Docker Compose to deploy your stack to Docker Swarm. Usually, if you reach the point where you need to scale your application horizontally, you would create a Kubernetes cluster and convert your Docker Compose setup to native Kubernetes objects. Alright, let's go ahead and start. First, let's create a folder for the Flask application. Flask is incredibly popular Python framework for building web applications, such as REST APIs. Now, let's switch to that folder and create a Python virtual environment. A virtual environment is used to create isolated space for your Python project with its own dependencies. This way, you can have multiple Python projects locally that use different versions of the same package, and this approach allows you to keep those projects separate. Now, it's not enough to install virtual environment. Every time you start working on the project, you also need to activate it. I use Z-Shell, and it shows on the left which virtual environment I'm using. Next, we need to install Flask into this project. I use latest 3.0 version. For this tutorial, it doesn't really matter, but if you encounter any issues, you can use $= to specify the version. Whenever you build artifacts, such as Docker images, you always want them to be reproducible. This means using the exact versions of packages that you used during development, rather than pulling the latest versions during Docker build. In Python, there are multiple ways to lock specific versions, but the most popular and oldest approach is to use a requirements.txt file. This is a text file, typically named requirements.txt, that lists all packages and versions you used during development. To create a snapshot of all current versions, use pip freeze command and redirect output to the file. At this point, we have Flask package and all its dependencies inside requirements.txt file, as well as a folder for the virtual environment. You should add this folder to your gitignore and docker-ignore files. Anyone who wants to work on this project would create their own brand new virtual environment and install packages from the requirements.txt file. Alright, let's create app.py file, which will be the entry point to our application. You should use this name since we'll refer to it in the Docker file. First, let's import Flask framework itself. Then we need to initialize app with the name property. Now, let's create our first endpoint. We'll use /about, which is a common path to return the version or some other metadata about running application. In Flask, you can whitelist the HTTP methods that you want to accept on a certain endpoint, like this. For our purpose, we only need get. Next, we need to define the Python function that will be responsible for processing this request. Let's call it about as well. In the function, we'll hardcode the version for now to 0.1.0 and return it to the client as a JSON object with a version key. You can also specify the HTTP status code. For this endpoint, we'll return 200, which means everything is okay. We'll also use /about endpoint later for the health check instead of creating a separate one. So it's important to return a successful status code. Now we can run Flask application locally and test it. One way to do this is to use Flask CLI, which is installed when you run pip install Flask. For the app argument, provide file name without extension and then use run command. Optionally, you can override port and the host, but we'll do it later. Remember, this is just a development server, which should never be used in production. Later, I'll show you how to use hot reloading for your Flask application without rebuilding the image. In a separate tab, let's use curl to test /about endpoint. At this point, you should use 127.0.0.1 and port 5000 instead of localhost. Alright, it works, and we got the hard-coded version back, which is a good start. Now, let's improve it a bit. Instead of hard-coding the version, we'll use environment variable. This is a common pattern to separate source code from environment-specific values. First, in Flask, we need to import OS module. Then, instead of hard-coding the value, we can get it from environment. Let's use app version for the variable. I'm taking shortcuts in this app. In real-world scenario, you would have multiple checks and validations for the variable. Now, go back to the terminal and run it again. If we try to get version now, it will be null because we haven't set the environment variable yet. Let's stop Flask and export app version variable. On Unix-based systems, you can also use env and grep to check the variable. Now, you can see we have the version. This variable is only specific to that session. If you open another terminal window, the variable will be gone. So you need to run Flask from the same terminal window. If you try to curl now, we get the version, which is exactly what we want. However, there is a problem with the environment variables. They are available to all processes running on that machine. Later, I'll show you a more secure way to provide sensitive data to your applications. Now, let's start containerizing our application. First, we need a Docker file. During this tutorial, we'll create multiple Docker files for this Flask application. For the first one, let's import Python, which is based on Alpine, a very small Linux distribution. We frequently use Alpine to reduce the size of Docker images. Next, we need curl. We'll use it later in the tutorial along with a health check. Then, let's define working directory. This sets a default folder inside the image where all your files will be copied. Next, we need to add dependencies to that working directory, represented by a dot. We won't copy Python files at this stage, because Docker images are built layer by layer, and those layers are cached. If the Flask application uses the same dependencies, and you only changed the source code, this step will not be rerun. This saves a lot of time, especially in your CI/CD pipeline. These small improvements reduce build time, and most CI/CD platforms charge by the minute, which results in a lower infrastructure cost. Next, let's go ahead and install all the dependencies. Finally, copy Python files inside the Docker image. If you have one or two files, you can copy them one by one using this approach. For a large Python project, you can use a dot or a star to copy the whole project. In the latter case, don't forget to create a Docker ignore file to filter out virtual environment and other unnecessary files from being included in the image. For the last step, we define command to start the container. In production, we frequently use this web server. We also need to expose all network interfaces and select a port. Before building the image, we need to add this web server to the dependencies. Let's go ahead and install it first. Then use pip freeze to update requirements file. We will no longer use Python virtual environment, so we can deactivate it. Just remember, if you want to add new packages, you need to activate it again. Before using Docker Compose, let's build the image manually. Usually, you would use your Docker Hub username, then the image name, image tag, and provide directory where to build. You don't need a Docker Hub account for this tutorial, but if you have one, you can replace my username. The build process will go step by step through the Docker file, executing all commands and installing dependencies. Now we have the image. When you start a Docker image, you get a Docker container. Use the following command to map application port 8080 inside the container to any port like 7070 on your laptop. Most of the time we use the same port, but if something is already using that port, you may need to use another one. To test, we can use curl. We no longer have to use 127 IP address. We can use localhost, which is the same thing, except it won't work when you run Flask with a default command. Also, we need to change default Flask port from 5000 to 7070, which we map to port 8080 inside the container. And it works, almost. We have not provided environment variable, so we got null in the response. One way to fix this is to explicitly provide variable in the docker run command. Let's give it a try. Alright, now we can convert this setup into Docker Compose. Let's go ahead and create a compose.yaml file, which is the recommended naming convention, but older options like docker compose.yaml are still supported for backward compatibility. Then we define top-level services element. Under this, you can create multiple applications. Flask, in this case, is arbitrary name for our service. Keep in mind that if you have multiple services, they can use this name as a DNS name to communicate with each other. We'll cover that later. Next, we define the image we want to start our application with. At this point, we're just converting docker run command into docker compose. I'll show you some tricks later to improve local development workflow. We'll map the same port 8080 inside the container to port 7070 on the laptop. Finally, we provide environment variable for the version. This is one way, and we'll cover more approaches later. Optionally, you can override the project name, which is mostly used as a prefix for Docker images, volumes, networks, etc. By default, it uses current folder name, which in my case is 199. In the real world, it's rare to see anyone using this name property. To run it, go to the top level and run docker compose up. This will run containers in the foreground, which is sometimes convenient because you can see logs right away. But you can use -d to run it in the background and use docker logs command to tail them. We'll do this later. As you can see, it will create a named bridge network. I have another tutorial covering all possible network drivers you can use with Docker, explaining each of them with examples. Then, Docker Compose starts a single Docker container and tails its logs. If we try to hit the same /about endpoint, we should get the version back. Now, what if you're actively working on this application and need to test it all the time? Let's change the version to app version. To test this, we need to rebuild the image. Let's go to the Flask folder and run docker build command again. This time, let's use latest tag instead of constantly incrementing the semantic version. Tags are not immutable, so you can override even a semantic version tag. But it's not a good practice. Some repositories, such as ECR in AWS, have option to make those tags immutable, which is a nice feature to have. Next, we need to change the tag to the latest. By the way, to stop compose running in the foreground, use Ctrl+C. Let's rerun compose. Test it, and we get the app prefix. So this is one way to update your app locally. As you can see, you need to perform two steps: build the image and then rerun docker compose. In my opinion, it's not very convenient. Let me show you another way. Now, let's define the build block. Similar to Docker build, we need to specify the context, which is a folder where all your files for that application are located. In our case, it's Flask folder. Optionally, you can specify Docker file to use to build this image. Docker file is the default, so you can omit this. But later we'll create another Docker file, so we'll use this to change the build steps. By the way, you can remove the image tag, and Docker Compose will use the project name and the service name for the image. Or you can keep it, and Docker Compose will use it to tag your image. I prefer to keep it, and later you can just push it to your repository. Now, let's change app version back to version. Instead of building images manually, you can use --build flag to force Compose to rebuild the image. You need this flag every time you change the source code. I'll show you hot reloading later in the tutorial, which means you can get the new app version without even rebuilding. To test, use curl one more time, and you should get the new version without app prefix. Let me show you other common ways to provide environment variables to containers using Docker Compose. We frequently use them to set different kinds of secrets and configurations. In the previous example, we hard-coded values directly in the Docker Compose file. This is fine for some configurations. However, you should avoid hard-coding secrets here because we always commit Docker Compose file to Git. This would expose your secret to anyone. To decouple secrets and configurations from Compose file, you can use the following approach. In this case, you only specify the variable name, like db password, without providing any value. Then you can create a file to define all your variables. This way, you can commit compose.yaml file to Git, but the environment file will stay local on your laptop or server. To set variables, use the same syntax. Additionally, in the Docker Compose file, you need to specify this environment file in your service definition. In this way, you source all environment variables from the file and provide them to the container. It's very straightforward, and you will frequently see this pattern in open source community when they provide a way to run something locally using Docker Compose file. Now, to test all those secrets, let's create another /secrets endpoint just for testing purposes. Initialize a Python dictionary called creds. We'll keep adding new secrets to the dictionary and return it to the client. First, let's test db password environment variable. We'll see if we can get it using this approach and store it in the creds dictionary. Finally, let's return the dictionary, which will be converted to JSON, along with the 200 status code. Let's run Compose one more time, and don't forget to use --build flag since we added a new endpoint. To test, let's hit /secrets endpoint using the same curl command. You can see we have DevOps123 database password. Alright, so this approach works. Now, let me show you a similar approach, but in this case, we explicitly set app token environment variable to itself. This is exactly the same as with the previous database environment variable, and you can add this variable to the dev.env file. The biggest difference is that if you forget to set app token environment variable, Docker Compose will show you a warning. This is very helpful if you're trying to debug something. Let's also get this variable and include it in the creds dictionary. Now, let's rerun Docker Compose with --build flag. You can see warning immediately if we forget to set this variable. In my opinion, this approach is safer. If you try to query /secrets endpoint, you will get empty string for that token. Another way to pass environment variables is to export them to the current session using export command. This is pretty much the same as we did with the plain Flask application at the beginning. Or you can set it like this before running Docker Compose up. Let's test it one more time, and it looks like it's working. We have the app token secret 123. Now, let me show you a more secure way of providing sensitive data to container. Environment variables often available to all processes, and it can be difficult to track access. They can also be printed in logs when debugging errors without your knowledge. Using secrets mitigates these risks. In a nutshell, we create a file with a secret, in this case API key, and mount that secret to the container. This way, only that container gets access to it. However, it's not very convenient in some cases because you have to read that file to get the secret, and some open source projects do not support this. After creating the file, we need to define it in compose file as a secret. Let's call it API key, which will be the file name mounted to the container. Then you just have a reference to that file that needs to be mounted. Additionally, we need to explicitly allow this Flask service to access API key secret. This is the short syntax, and I'll show you a more verbose one later. Here, we just need to provide the secret name. Now, in the application itself, we need to read that file from the disk. The default location is /run/secrets/secret name. We'll change it in a bit. Let's go ahead and rebuild the Flask container. If you try to use curl, we'll get API key query2-123. Unfortunately, you can't automatically expose those secrets as environment variables, but you can change location. This is very helpful, especially when you're using open source tools or databases that expect a secret file at a specific location. To change the mount path, we first need to specify the source file and then specify the target path. In this case, we mount the same API key secret to two different locations. Let's get the second API key from the custom path and insert it into the creds dictionary. Alright, we can rebuild the image one more time. If you hit /secrets endpoint again, you'll see two API keys. Next, let's talk about configurations. The goal is to separate application source code from environment-specific values. For example, in a development environment, you may need to use a development database. In production, you would use a production database. These databases would have different hostnames, users, etc. This way, you no longer need to rebuild your Docker images for each environment. You can simply supply configuration and let application read them. Let's go ahead and create a very simple YAML configuration file with a single env key. In the real world, you can use JSON, YAML, or other file types, and the configurations will be much larger. Traditionally, we mounted these configurations to the containers using volumes. This means mapping a file on your local file system to the container's file system. The path should be relative to Docker Compose file. For example, in VS Code, you can copy relative path. On the right-hand side, you specify where you want to mount that file. I'll put it in the root and give it the same name. Usually, you would not use environment suffixes in the file names you mount inside a container. Your application in all environments would read the same config.yaml file. Now, in the Flask, let's create another /config endpoint to test if we can read configuration files. We'll create a config dictionary and keep adding new configurations as keys. This is just for testing, you wouldn't have these endpoints in real application. Let's go ahead and rebuild the Docker image. If you use curl to hit /config endpoint, you should get your config back. In the new Compose version, you can also use config's top-level element to do exactly the same thing. API is similar to the one for secrets. Let's create a new myconfig and reference the same file. The next step is to add config property to the Flask service. You can use short syntax similar to secrets, and your config will be mounted to /config name location. Or you can use a more verbose syntax to specify the location where you want to mount it. Almost all open source projects expect a configuration file in a specific location. In this case, we'll mount the file to config dev v2.yaml. To test, let's read that file and include it in the config dictionary as well. Next, we need to rebuild the image and start compose. When you try to access /config endpoint again, you should have two configurations returned to you. Let's talk about how you can persist data between container restarts. By default, anything you store inside the container will disappear if you destroy that container. Therefore, you need a way to persist data for stateful applications like databases. There are two main approaches. We'll start with the oldest one, which is bind mounts. Using this approach, you bind a directory or a file from your local file system to the container. This is similar to the configuration we used before. When you bind your local folder to a folder inside the container, everything the container saves in that folder will be stored in your local directory. Now, let's go ahead and test this. First, let's import requests from Flask. We'll create another /volumes endpoint that we'll use to test persistence. This endpoint will accept both GET and POST requests. If we receive a POST request, we want to save some data to test.txt file. We can use Flask to check the type of the request. If it is a POST request, we first ensure that /data folder inside the container exists. If it doesn't, we create it. Then we create test.txt file, write customer record into that file, and return saved message with 201 status code. On the other hand, if we receive GET request, we read that file from the disk and return its content to the client. So we use /data directory inside the container to persist customer data. Now let's go ahead and test this. We need to rebuild the Docker image to include /volumes endpoint. To send a POST request, we can use curl with additional flag. In this case, we don't need to send any data along with the request. Alright, we got a response that the customer record was saved in the test.txt file. Now, let's change the POST request to a GET request. This time, our application was able to read the test.txt file from the disk and return the content to us. When using Docker Compose, you can either stop the containers, and in that case, all data inside the container will be saved. For example, when you cancel Compose using Ctrl+C, the Flask container will be stopped. To restart it, just run Docker Compose up again. If you try to get customer data from the container, you'll get it back. This might be a bit confusing, but you should not rely on this behavior to persist data. Most of the time, you will remove and restart containers using Docker image, and in that case, you would lose all your data. Let me show you. Now, just run Docker Compose down, and in this case, Flask container will be removed along with all data saved in that container. Let me restart it again. If you try to get customer record from the container, you will get an error since the test.txt file no longer exists. To create that record, we used a POST request. So that's the problem. Some applications, such as databases, need to persist data between restarts. Alright, let me show you the first and oldest approach of binding a local directory to the directory inside the container. Inside the compose file, select arbitrary directory, for example, my data. This directory can be at the same level as the compose.yaml file, or you can create it inside the Flask directory. Just don't forget to add it to your gitignore file. So on the left-hand side, we have my data under Flask directory. On the right-hand side, we bind this directory to the containers/data directory. Everything the container saves in that directory will also be saved on the local file system. Let's run Docker Compose down to start with new containers. Now run Compose up one more time. Whenever you send a post request, this time the customer record will be saved on your local file system. You can see the test.txt file inside my data directory. To test this, let me stop and remove containers with compose down. Now let's run compose up again. And if you try to send a GET request, you should get the customer record back. This way, we validate that bind mounts work, but they have some limitations. A preferred approach would be to use Docker volumes to persist data. There are several advantages such as easier backup, management through Docker CLI, and safer sharing among multiple containers. You can read more about advantages here. Alright, let's go ahead and test volumes. First, we need to comment out the bind mount, since we will no longer use it to persist data. To create a volume, just use volumes top-level element and give it a name, like Flask data. To mount that volume, we use the volume name on the left-hand side and the target directory on the right. We'll mount to the same /data directory inside the container. Now, let's go ahead and remove all containers. This time, let's run it in the background by adding -d option to the docker compose command. To get all volumes, you can use docker volume ls. This command will return all your Docker volumes. You can also use inspect command to get more information about the volume. Now, at the bottom, let's use curl to send a post request to create a customer record. Then we need to remove Flask container to make sure this approach works. Alright, let's run it one more time. If we send a GET request, we'll get the customer data back, so that means volumes work as well. I suggest you use volumes instead of binding a local directory to the container file system. Now, when you're working on some feature, you want to get feedback as soon as possible. Yes, you can rebuild the image every time you change the source code, but let me show you another way that does not require rebuilding anything. It's very framework specific, but you can apply similar techniques to other languages and frameworks. So first, let's go ahead and create another Docker file that we will use for hot reloading. It's very similar to the previous one, but we copy all the files using wildcard and start Flask using Flask CLI instead of a web server. Next, we need to update Docker file that we use to build our image. We also want to run Flask in debugging mode, so that any changes you make are immediately updated in the container. For that, we need two environment variables: enable debug mode and specify the Flask entry point, which is in our case app.py. Then, under volumes section, we want to map the entire Flask folder to the working directory inside the container. The last thing to note is that since we copy all files in the project to the container, we need to avoid copying some internal folders like Python virtual environment, which can conflict with container environment. For that, we create a docker ignore file, similar to gitignore. We can Google some examples of docker ignore files for Python, but mostly we want to ignore virtual environment. Let's grab the first example we find and copy everything to our project. As I said, the most important part is to ignore virtual environment. Alright, let's go ahead and rebuild the image. You can see that the Flask is now running in debug mode. If you try to hit /about endpoint, we'll get the version. Now let's add app prefix to the version just for testing. Whenever you save that file, Flask will immediately reload your application. So there is no need to restart Docker Compose or rebuild the image. And now you get app version. This approach should only be used for development and debugging. Don't use this Docker file to build Docker images for production. In this part, let's deploy Postgres and integrate it with Flask application. We'll follow best practices and provide the database password as compose secret. First, we need to create a file and come up with the password. Next, define the secret and specify the path for that file. This secret is located at the same level as compose file itself. Finally, create a volume for the database. You don't want to lose all your data if you restart your Postgres. Let's also create a network for both the Flask and Python applications. This way, they can communicate and use service name as DNS name to discover each other. Let's call this network private, and by default it will use a bridge network. I have another video explaining all the different network options for Docker. All other parameters are optional. For example, you can explicitly select a driver. You can also optionally provide a seeder for that bridge virtual network, and all your containers will get IP addresses from that seeder. Now, let's create a Postgres service. We'll use the latest 16.3 Postgres version. Optionally, you can expose ports to the localhost, but it's not necessary for the Flask application. By default, all ports are accessible in that virtual network. Only map Postgres port if you plan to run Flask locally without using Docker Compose. Next, we'll use environment variables to set some secrets. First, let's create a user and MyDB database. For the password, let's provide location of the secret in the container. This file suffix indicates that Postgres will take that path, read the file, and use its content as the password. Next, we need to provide the secret we created earlier. For the persistence, bind our Postgres data volume to the data directory inside the database container. Place this database in the private network that we just created. Additionally, let's place Flask application in the same private virtual network. At this point, we can run compose app in the background. This will spin up Flask and Postgres database containers. To check running containers, you can use docker ps command. We need to SSH to the Postgres container to create a user and a table for the Flask application. Use the following command and update container name to match yours. First, let's create a table for the items. Since it's to-do app, we need item ID, priority, and the task itself. Next, we need to create a user for the Flask app. Then grant all necessary permissions to that user. The next step is to install Postgres driver into Flask application. Before that, don't forget to activate Python virtual environment. We need both binary and connection pool packages. Make sure to get a snapshot of those packages and save them to requirements.txt. In app.py, let's import connection pool. We need to create a function to initialize connection with the database. Get the host, database, user, and password from environment variables. Then create a connection string and connect to the Postgres. Don't forget to return connection pool, since we'll use it to insert and select items from the database. Call this function right before initializing Flask application. Next, we'll create a couple of functions. The first one will take item and save it in the database. The second function will return all items in the database. Finally, let's create another /items endpoint. If it's a POST request, we'll save the item to the database. If it's a GET request, we'll select all the items from the table and return them to the client. We still need to create a few more environment variables for the Flask. We need Postgres hostname. In Docker Compose, you can use the service name as a DNS. So we simply match the environment variable with the Postgres service name. Next, we need a database and a user. Alright, we can deactivate virtual environment and rebuild the Docker image. We need to rebuild it since we added additional Python packages. To create an item in the database, you would send a POST request. Let's create another one as well. To get all items from the database, just send a GET request. You can also SSH into Postgres and select all items from the table. In this section, we'll deploy Nginx in front of the Flask application and use Nginx as a load balancer. In our case, we only have one Flask instance, but you can scale it to multiple instances. This is a common pattern you can see in production environments. First, let's create a dependency. We want to start Flask application only when the Postgres database is already running. The first option, in my opinion, is not very useful. It simply defines the order in which the containers should be created. For example, we want Flask container to be created after Postgres container. However, depends on by itself does not check if the container is running, let alone if Postgres is healthy. It works in this case only because Postgres driver in Flask application has 30-second timeout to wait for the database. So this particular dependency is not very effective, but I want to show you that this option exists. We'll implement a better option a bit later. Next, let's create Nginx configuration to load balance traffic. We need to define upstream service and give it a name like myapp. Then list all the backend servers. In our case, we only have a single Flask instance. By default, Nginx uses round-robin algorithm, but you can configure it to use different algorithms as well. I have another video explaining different load balancing algorithms with Nginx examples. For the location, we use upstream service. Let's use compose config top-level element to define it. To improve security, we can create additional virtual network and call it public. We'll place Nginx and Flask in the public network and keep Postgres database in a private network. This way, if your Nginx gets compromised, it's not possible to reach Postgres from the Nginx container. Now, let's create Nginx service itself. We'll use the latest Nginx image based on Alpine. For the Nginx, we need to map ports 8080 inside the container to 8080 on the local host. In this case, we need to mount Nginx config to a specific location inside the container to override default config. Let's place this container inside the public network. We also need to update Flask service and place it in both the private network and the public network. The private network is needed to reach database, and the public network is needed so that Nginx can forward traffic to it. We no longer need to expose Flask or Postgres ports on localhost, so we can remove them. Finally, let's create a proper health check for the Flask application. We want to start Nginx only after Flask application is not only created, but also healthy and able to accept requests. Instead of creating a separate health check in our application, let's reuse /about endpoint. The main requirement is that endpoint should return successful status codes between 200 and 300. It's very straightforward. As you remember, we installed curl inside the Flask image, and we can use it to hit /about endpoint. If the status code is between 200 and 300, the service will be marked as healthy. We also need to create a depends on block and only start Nginx when Flask is healthy. Alright, that's pretty much all. Let's go ahead and start Docker Compose. You can see that Postgres container is created first, followed by the Flask container. Then Compose waits for the health check to complete before spinning up Nginx container. As soon as curl hits the /about endpoint, Flask will transition to a healthy state, and Nginx will start right after it. Now we can test by hitting Nginx on port 8080 and it should work. In the logs, you can see that the request went through the Nginx proxy to Flask. Let me show you the container networks. You can run docker ps or docker compose ps to get all running containers. Let's go ahead and inspect Flask. The Flask app will have two network interfaces, one in the public virtual network and another in the private virtual network, each with distinct IP addresses. Now let's SSH into Nginx container to check if you can reach Flask and Postgres. Use the following command to check if the port is open on the Flask app, ensuring Nginx can access it. Now, let's see if the Postgres port is open for the Nginx. It says that Nginx cannot resolve Postgres DNS. If you try to access Postgres by its IP address, you'll get a timeout. Now, let's see if we can resolve Flask. Yes, we have IP address from the public virtual network. As expected, we cannot resolve Postgres to the IP address, since it's located in different virtual network. In this section, we'll secure Nginx with a Letsencrypt certificate and prepare for production deployment on a single Linux server. We'll also automate certificate renewal using Docker. You can do this at home using the public IP address provided by your internet provider, or you can set up a virtual machine in the cloud. In this video, I'll show you how to do it in AWS. However, the process is very generic and works in many other environments. First, let's declare a few environment variables for certbot. It's very important to use your real email address here. If certbot fails to renew your certificate, Letsencrypt will send you a warning to that email ahead of time. You can also select how often you want to check if the certificate needs to be renewed. Letsencrypt issues certificates that are valid for 90 days, and approximately every 60 days, certbot will automatically renew them. The default is 8 days, which is fine and you can keep it. You can also tweak other parameters. I highly suggest setting staging environment variable to 1. This means you'll use Letsencrypt testing environment to issue certificates. Once you verify that you can get a certificate, set this variable to 0 to use a production environment and issue real certificates. Letsencrypt only allows a limited number of certificates per week per domain, so you could exhaust that limit while testing. Next, create a similar Nginx config, but this time specify TLS section. We'll still declare my app upstream service, but now we need to listen on port 443. You don't need to set up a redirect from port 80 to 443. It's done automatically for you. It's important to replace domain with your own and preferably use the domain in the path where you want to store a private key and certificate on the file system. That's pretty much it. You can use the same approach for the front end, such as React or Angular apps. Before we add certbot, let's make sure our Compose services are ready for production. Set restart to always. This way, if a container crashes or exits, it will be immediately restarted. This setting is necessary in the cloud. For example, if your virtual machine, such as EC2 instance, restarts, this setting ensures Docker will bring back all the services once Linux starts. It's similar to the systemctl enable command. Next, we need to change Docker file. We'll use the one that does not support hot reloading and optimized for production use. I discovered a weird behavior on Linux that overrides environment variables provided in the config with null values. So let's comment them out and get values from the env file. We also need to declare a new Nginx config with TLS section and comment out the old one since we'll no longer use it. Nginx needs to obtain and store private key and certificate locally on the file system, and we want to persist those files between restarts. Otherwise, after each restart, Nginx would need to issue a new certificate, and you may quickly reach the limit. So let's create a volume for the Nginx to store the key and certificate. To automate TLS certificate, we'll use a slightly modified Nginx image. You can use it as is or build your own following provided instructions. It's a relatively popular project and very well maintained. Now, we need to expose port 80. HTTP 01 challenge uses that port to provide token back to Letsencrypt and prove that we manage that domain. We also need to expose port 443 for HTTPS. As I mentioned before, Nginx will automatically redirect any HTTP requests to HTTPS. Next, let's mount our Nginx config to a specific location inside Docker container. For persistence, we need to add a volumes section and mount that volume to etcd/letsencrypt. This is the default location for the certbot to store certificates. We also need to provide all environment variables we declared at the beginning, including your personal email address. You can use docker compose config command to verify that all environment variables are sourced and available for the containers. This is a useful command for debugging. Now, let me quickly create EC2 instance in AWS. You can use any other cloud provider. It's very generic. Let's go ahead and launch EC2 instance. Give it a name like My App. Select Ubuntu LTS long-term support version. You can keep T2 Micro instance, which is even eligible for the free tier and sufficient for testing. Next, we need to create a key pair. The public key will be saved in AWS, and you should keep private key secure on your laptop. You'll use this private key to SSH into Ubuntu instance. Next, we need to open port 80 for HTTP 01 challenge and port 443 for HTTPS. That's pretty much all. Go ahead and click Launch Instance. In this case, we use default VPC. All subnets have a default route to the Internet Gateway, and virtual machines will automatically get public IP addresses on launch. Let's wait a bit until EC2 instance transitions to running state. Under Security tab, double-check that you have opened all necessary ports, otherwise you won't be able to get a certificate. Port 22 is used to SSH into the instance. If you want, you can limit the source for the port 22 to only your public IP address. Next, we need to get public IP and use it to SSH into EC2 instance. Before we can SSH, we need to change permissions on the private key to be accessible only by our user. Then you can SSH using the private key. The username is always Ubuntu, and you will need to update the public IP address of the EC2 instance. Next, we need to install Docker on Ubuntu. The easiest way is to Google it, and you'll be directed to the official Docker website with installation instructions. First of all, we need to set up Docker repository. Copy, paste, and run provided commands on the remote Ubuntu server. Next, we need to install Docker itself, including all dependencies. Again, copy, paste, and run commands on the server. If you try to use Docker, you will most likely get a permission denied error on Linux. To use it, you would need sudo to execute any Docker command. To fix this on Linux, follow these steps. Make sure you have a Docker group. Add your current Linux user to the Docker group. Reload group settings using the specified command or start a new session. Now you can run Docker without sudo. Next, we need to copy all the files to the remote server. You can manually copy Docker compose file and other configurations, or you can use rsync command, which is my preferred approach. You will need to change the key location and the IP address of the remote server. Also use current directory to copy all files, including Flask application, to Ubuntu. At this point, we have all the files on the EC2 instance. You can run docker compose config one more time to ensure all your environment variables are loaded in the compose file. This is useful because Docker on Linux has slightly different behavior. Make sure you provide your real email and start with a staging environment. Also, double check that database password is present. For the first time, I suggest running Docker in the foreground. You don't want to miss any errors. If you uploaded your Docker image to Docker Hub, it will simply pull it from there. Otherwise, it will rebuild the image locally. For example, if you don't want to copy Flask application, which I would not suggest for production use, just make sure that you pushed the image before running Compose up. You can also remove the build block. Alright, Servbot will generate a private key and certificate request, and will try to request a certificate from Letsencrypt, but first it will fail. You can see the issue. We didn't create a DNS record to point to this EC2 instance public IP address. Let's go ahead and fix it. It doesn't really matter where you host your domain. You just need to create a record and point your domain to the server's public IP address. In my case, I use Squarespace domains, but every single DNS provider supports A records. Usually it takes a couple of minutes, but in edge cases it may take up to 24 hours to update DNS. You can use dig or NSLookup to verify your DNS record. After you can resolve your domain to the public IP address, we can go back to Docker Compose and rerun it again. Let's also run it in the foreground for now. It will take a few more minutes to get certificate. You'll see that Servbot will try to renew it in 8 days. You'll also see a message in the logs indicating that certificate was successfully issued and stored locally. Let's open a browser and test if we got the certificate. You'll see a warning because this certificate is for testing only, as we used staging Letsencrypt environment to obtain it. Make sure you can get this test certificate before switching to production Letsencrypt environment. Alright, let's set staging environment to 0 and try to get real certificate. If you change this locally, don't forget to run rsync command again to copy the file to the server. Let's print the file on Ubuntu and make sure the staging environment variable is set to 0. Now, let's destroy all the containers. Optionally, you can remove the volume where certbot saved the staging certificate and the private key. This time, let's run Docker Compose in the background. You can use the following command to tail the logs of all containers in the compose file. Certbot will generate a new private key and certificate request and try to resolve HTTP 01 challenge. Since we already created DNS record, we just need to wait a few minutes. Alright, you can see that we got a new real certificate. It will also be scheduled for renewal every 8 days. This does not mean that certificate will be renewed every 8 days. It only means that certbot will check if it needs to be renewed and obtain a new one if it will expire in less than 30 days. We can test it one more time in the browser. This time we shouldn't see any warnings. Let's go ahead and check certificate. You'll see that certificate is valid and will expire in around 90 days. Also, let's test HTTP to HTTPS redirect. It should work as well. Now, let's test that restart policy also works. We can get all running containers with Docker PS. You'll see that uptime is about 2 minutes. Now, let's restart Ubuntu server and see if Docker Compose will start containers automatically after reboot. Wait a few minutes and SSH back to Ubuntu. Now, you can see that Docker Compose started all the services immediately after reboot, and the uptime is only a few seconds. If we try to curl our Flask application over the internet, we get a response. If you want to scale your application, I highly recommend learning Kubernetes, which is de facto standard for container orchestration. Also, I have benchmarks on my channel and other tutorials. Thank you for watching, and I'll see you in the next video.